Hello,
Oh, yes, sir. Good evening, sir.
good evening. Uh, so I think the questions that you asked they are from assignment, right? Some assignment.
Oh, yes, sir. Yes, these are assignments.
I think nine, week number nine. Anyway, it is.
Yes, sir.
We will take them towards the end, but we already discussed this fluid kinematics in one of the earlier
Yeah,
classes.
yeah.
So
Actually, sir, I have answered them, sir, but I just want to confirm.
yeah. So first we'll finish the some of the remaining part in the last class regarding the.
Right, sir. Yeah, yeah.
So we had covered most of the topics there, but two topics are still remaining. First is mm, minor losses in pipe flows or pipe flow, I should say. So basically, uh, we can take one example that will give you some idea. If you remember this, that's it. There is not much uh, this thing in this topic, not that difficult of things. So, for example, and this type of questions are typically asked also from this topic. So, this is like extension to the problem solving part. So, let's say you have a very large tank and you have a small outlet at the bottom, and then there is some extension. And finally, there is a, let's say, 190-degree bend. And then there is exit. So, and this is a fairly uh, significantly bigger pipe. So don't worry about the variation in the height of the pipe, etc., height of the tank, etc. Uh, so this actually should be 1 second. Yeah, this should be somewhere here, like that. So water is flowing like this, like this. Then there is a bend, and it goes to the atmosphere. So uh, in the last class we discussed. Maybe I'll use some different colors to just highlight uh, different parts. So uh, let's say this was length L1. Oh, maybe I should use black for this. Maybe later I use the. So from the exit of the tank, let's say this is L1, and then you have some length L2 where the cross-sectional area increases, and then you have some length L3 which is still the center of the bend, which is again a straight flow. Then there is a curvature, and then you have L4, which is your exit length, exit portion pipe length. You can take D1, D2 accordingly, no issues. So this example covers mostly all of the minor losses, and therefore I have taken this. So first of all, uh, so what is happening is liquid is entering from the pipe into this small cross-sectional area. So there you will have uh, entrance loss and this is a loss in pressure or loss in head, okay. And then what happens? Then the water flows through L1 length. So this entrance loss is a minor loss. Then here you will have the typical loss that we considered in the last class, which is called as F1 L1 V1 square by 2GD1. So this is the typical Darcy-Weisbach equation loss, head loss, and this is actually a major loss. Then the fluid, and this, let's say this is your D1 and it is the velocity V1. So from previous classes we know V1 will be equal to under root 2gh, and h will be the height of this tank level till the center of pipe, let's say. So from there you calculate V1. Now what happens? There is an expansion here. So the liquid which was flowing with some velocity V1, now it enters into a enlarged cross-sectional area. So here there will be expansion loss. This is also minor loss. And yeah, sorry, I should have mentioned here earlier. Entrance loss is typically 0.5 times what is the velocity in the next section divided by under root 2g, since we are talking in terms of heads. Typically that is the entrance loss. So where it is entering, like from larger to smaller diameter or cross-sectional area, that smaller velocity will be high. So that velocity you take, and 0.5 is typically the constant that is multiplied. In some other questions, they can specify the constant differently. Instead of 0.5, they may say it is 0.4 or something, but typically it is taken as 0.5. Then the expansion loss, it is typically calculated as, let's say, when the water enters in the L2 section, it has a diameter D2 and velocity V2. So this expansion loss is typically V1 minus V2 square by 2G. Since you are taking the square of the difference, it doesn't matter, V1 is greater than or less than V2. So like that. Now what happens? Liquid flows through this D2 cross-sectional area, enlarged cross-sectional area, and again, yeah. So in this length, the L2 length, there will be another major loss, which will be F2 L2 V2 square by 2G D2. So there will be another major loss. The reason why we call them major and minor losses is, if you calculate these values, what you will observe is the major losses, which are FLV square by 2GD terms, their values are significantly higher than the other minor losses, which are entrance loss, expansion loss, etc. So therefore they are called as minor losses. There is no other reason for that. And after that, what happens? The water enters into the cross-sectional area where the diameter.
Can you repeat the statement that you gave just now? Where they are called minor losses?
Yeah, so maybe when we'll solve some examples later, then we can do the calculation. So what happens? Typically, this length, like FLV square by 2GD formula that we use for a straight pipe, the length and the diameter are, like, length is very large. Typically, it is of the order of some meters, and diameter is of the order of some centimeters or something like that. So when you do the calculation, this FLV square by 2GD term, it will have some value, right? Some quantity. That value will be typically larger as compared to the minor losses, which are like entrance and expansion losses. So that's why they are called as minor, because their impact on the overall head loss is not as significant as the FLV square by 2GD terms. But still, in some cases, you need to consider them. I mean, strictly speaking, this is not a correct classification, major loss, minor loss. but it is a convention, because let's say if I only have one length FLV square, we will take one small derivation after this. So maybe there it will become clear. But conventionally, they are called as head loss, minor head losses, and FLV square 2GT terms, because typically their values are significantly higher, they are called as major losses. Sorry. So coming back to this, so now liquid enters from D2 to D3. Again, there is a contraction loss. So here also you consider one entrance loss, which will be equal to 0.5. Now it is entering into the V3, right? D3 section, so it will be V3 by 2G. Wherever it is entering, that velocity you have to take. And then again, similar to what we observed in the second pipe, here will be one major loss because of this length. It will be F3 L3 V3 square by 2G D3. It is the part of major loss. Now there is a bend. After the flow through the L3 length, there is a bend. So typically, this bend is also considered as loss due to bend. This is also considered as a minor loss, and it is typically some constant into here the velocity will be same only. But again, if there is a bend in which cross-sectional area is changing, some sort of wall or some sort of reducer, typically you take the higher velocity so that you will capture more loss. Here the velocity will be same only since the diameter is same. So it will be some constant K, and K typically varies between, let's say, point, maybe I should use more space. K typically varies between 0.3 to 0.8 or something. So it is, the value should be less than 1 is the point. In some cases it can be greater than 1, but that is highly unlikely case. So typically it is less than 1. So now again there is a flow through L4 length, so that will be considered as major loss. So this will be F4 L4, and V3 and V4 are same only, so I can write V3 square by 2G D3, since D3 and D4 are also same. This will be our major loss. And finally, last but not least, when fluid is going into the atmosphere, it is exiting the pipe, right? So there will be expansion loss again. So here one expansion loss will come. That is again minor loss, and it is V3 minus 0 by 2G. So basically you assume when the fluid goes into the atmosphere, it comes to the rest, and that happens typically. Like up to a certain point it will have some velocity, but then it will come to rest because of the air drag that is exerted on the fluid. So like that. So maybe I can summarize for you some like minor losses when they are called. Typically they have entrance loss. It is 0.5 V square by 2G, and V will be the velocity where it is entering, so maximum velocity. Then there will be expansion loss, that is typically V1 minus V2 square by 2G, and then there is last loss due to bend, and that there is no constant for that. It is typically some constant K into V square by 2G. Here also you take maximum velocity between the two values if there is a change in the cross-sectional area across the bend. So this is basically the idea behind it, and other major losses are same as the last time we discussed. So if the fluid has to flow from this type of variable cross-sectional area pipe, and it has a bend also, then there will be these minor and major losses. These losses fluid has to overcome, otherwise it can't flow from let's say point A if you consider point A here to point B, which is at the exit. So if the fluid flow has to take place from point A to point B, fluid needs to overcome this much pressure loss. If it can, then it will be possible flow, otherwise flow will not happen. And that is decided by the height of the tank, because V1 is under root 2gh. So like that the question is there. Now we will take one this thing. Let me just 1 second find it. Yeah, so typically what happens, let me just find the question also if I can. Give me a couple of minutes. It is actually very commonly asked questions, and sometimes in some competitive exams they assume that you know the derivation and they ask you the question, but you should like you should have seen these three. If you have seen this earlier, then only you can answer, otherwise you can't. So the question is, like, there is a tank, there is only one pipe. Yeah, so question is, for maximum power transmission through a pipeline with total head, capital H, head loss due to friction HF is given by, and you have four options: capital H by 10, second option is capital H by 3, third option is capital H by 2, fourth option is 2H by 3. This is a very common question, and like, if I have not mentioned, but these all major losses, minor losses, they are all losses due to the fluid friction between the pipe and the fluid. So as I said earlier also, for power transmission, power transmitted through the pipe, formula remains same. It is rho g q h net. So what is the total head, net head across the pipe boundaries, inlet and outlet, and multiplied by rho g q. So basically it is mgh, like m dot gh, basically energy per unit volume. So that way you can remember this formula. But here the total head is actually capital H minus frictional head, right? And you can imagine it something like this. Let's say there is a tank. It's a very big tank. For the purpose of drawing, I am drawing it small, but assume it a large tank, and there is a water level up to very large height, which is actually given as capital H in the question. Total head is given here, the capital H. Here you can put any pump also, okay? You can, at the inlet of the pipe, you can put pump also and calculate how much the pump head is there, because every pump is also defined by the maximum head and maximum flow rate, if you have seen any pump. But anyway, just for the simplification, we are taking a large tank, and at the end you have some pipe of length, let's say L, and diameter, let's say diameter D. Okay. And at the end, fluid is coming out into the atmosphere. So here, what is your total HF, which is head loss due to friction? So HF will be, there will be one component of this, right, entrance loss. One second. Yeah, so there will be one component of entrance loss at section, let's say I will point section 1, and let's say the exit is at section 2. So at section H1, you will have head loss, which will be that is entrance loss, right? So entrance loss is 0.5 V square by 2G, and then it flows through a pipe, then it will be FL, same velocity because same pipe, FL V square by 2GD, and when it goes out in the atmosphere, it is expansion, but expansion with velocity at the last, like when it goes to the atmosphere, we assume that its velocity reduces to zero. So this is your total head loss, right? So it will be 0.5 V square by 2G, and there will be 1 V square from the last term, so it will become 1.5 plus FL V square by, maybe I'll write L as capital L, by 2GD. So this is your total head loss. So in this question, they have not given the assumption in the language of this question, and that is what I was trying to say earlier. Here the assumption should be given as, you know, one second. Yeah. So here there is an assumption that neglecting minor losses, because if you don't make that assumption, you will not get any of the option as the answer. I'll show you how. So let's not worry about that assumption. Let's solve the problem. So we'll call this power as P. So what is your P now? Therefore P is rho G Q into FLV square by 2GD plus 1.5 times V square by 2G. And we know that Q is nothing but cross-sectional area, which will be pi d square by 4 into velocity, right? Since it's assuming circular pipe. If nothing is given, we assume circular pipe. So therefore, your P is nothing but rho G pi d square by 4, this area term, and velocity will go inside. So it will become V cube 2GD plus 1.5 V cube by 2G. Okay. I hope this is clear. Now see, density is constant, diameter is constant, length is constant. So only variable here is velocity. So basically, this is a function of velocity. I should not write new. This is a function of velocity. So we know from our maths that if you want to find out some maxima or minima of particular function, you take the derivative with respect to that function, with respect to the variable that is controlling that function, equate it to 0, and then you check the second derivative. If that is negative, then it's a maxima. If the second derivative is positive, then it's a minima, right? So we'll do that here only. So we'll take the derivative of power with respect to the velocity. If you do that, see, the constant term will go, right? Because this rho g pi d square by 4, it's a constant. It won't change anything. But inside you will have FL 3V square by 2GD plus 1.5 times 3V square by 2G equal to 0. you solve this, you can take 2g 3 common, then what will you get? Okay. Yeah. 1 second. H minus HF, right? Oh, sorry. Here, see, this is only H, right? Capital H, we left it only. So, 1 second. This will be rho GQ as it is, but here it is capital H, because you will, the actual power is rho GQ and head loss, net head loss, which is capital H minus all the small losses. So that term I missed. Anyway, it doesn't change the description, only the maths will have some extra terms. So now one H will, V velocity will come here also, because you are multiplying it with the area, which is pi d square by 4 into velocity. So again, this remains the function of function of velocity only, no change. Yeah, the only change here will be you will have one H minus, and this will be minus. That's it. So there is no change there. So okay, yeah, that's what I was wondering, because there was no capital H. So yeah, otherwise you won't get anything out of this. So now again, from here what you have, you can take H on the one side, and here you have, let's say I take 3 common, and what remains in the bracket? FLV square by 2GD plus 1.5 V square by 2G. So if you do that, and let's go back to the equation number 1, what you observe is it is nothing but HF. Therefore, H becomes 3 into HF. So even though this assumption was not there, neglecting minor losses, we are getting the same answer. So your HF should be equal to H by 3. Now, as I said in the some time back, that when you equate like first derivative to 0, this can give you either maxima or minima, right? So, but in the question it is asked that what is the maximum power transmission. So to check that, what you need to do is you need to check d square p by dv square, which is nothing but derivative of dp by dv, one more derivative basically. So we need to take derivative one more time of equation number 2 with respect to v. So here h term, capital H is constant, so it goes to 0. FLV square will have, this will be minus 6 FLV hoga by 2GD, then again minus, then 1.5 into 6, 4.5 into 2, so 9V by 2G. So if you see that all the quantities in this equation are physical quantities, so they cannot be negative. So this whole quantity is negative of 6 FLV by 2GD plus 9V by 2G. So this is a positive number, right? And since it's a negative, therefore your d square p by dv square is negative. Therefore HF equal to H by 3 gives maximum power P. So this is your answer. So this is very commonly asked question. I can remove this assumption even though it was not mentioned in the question. It's fine both ways. See, if you neglect minor losses in equation 1, you 1 second, I will use this laser. So if you neglect minor losses, now only this 1.5 v square by 2g term goes, rest of the equation will, rest of the derivation remains same. Only these terms will not come. But we have considered them, and then also we are getting the same answer only. So this term will not be there, but still it doesn't matter. You should remember that for maximum power transmission, the friction head loss will be 1/3 of the total head loss. Okay, so this is one thing.
Actually, sir, mostly, sir, I have seen other problems, similar problems. So I think they reply mostly that the denominator is always 3, sir, mostly, in most cases. Even 3, like 4/3, so something like that.
In fluid mechanics or somewhere else also?
Fluid mechanics, sir, mostly, yeah. The similar problems will have generally HF becomes mostly something by 3.
Okay. Yeah, it can happen. Mostly it will be like 1/3 or 1/2 or 2/3, something like that. But anyway, in this case it is h/3. So keep that in mind. This will save you a lot of time in some competitive exam. Otherwise, there is no time to do derivation, etc.
So this is general. This is general thing that means.
Yeah. General for this type of arrangement. If there is some bend or some expansion or something in the pipe, then you can't do that. Then you have to solve it like the what I've done initially here.
Yes, sir.
This clumsy figure is there, but hopefully it makes sense.
Yes.
Okay, then regarding this pipe loss, there is one more very common question. Let me just take it. It's very common. I have seen it multiple times. Yeah. So So the question goes something like this. This is previous year ESE question. The head loss in sudden expansion from 6 centimeter dia to 12 centimeter diameter in terms of velocity V1 in smaller dia pipe is. So I'm not giving options because we'll solve it. So we'll take a typically sudden expansion, right? So initially there will be a small pipe length and it will be suddenly becoming something like this, and then there will be a larger dia flow. So let's say we'll solve it for a general case. We can put D1, D2 later. So let's say this is D1 and this is your D2 and this is your direction of flow because it is sudden expansion. It should be from smaller to larger. Let's say it was V1 here and V2 here. So it is, going like this. And since this is the expansion area, there will be some pressure loss, some vortices, etc. will form here. Anyway, so now let's call expansion as expansion. I'll use EXP as the short form, and we know the formula, which is V1 minus V2 square by 2G. So this is the head loss due to expansion. Now let's see. It is asked that in terms of V1. You can do the algebra in terms of V2 also. It doesn't matter. But what is important is we know that the total flow rate is, maybe I should write A1 V1 is equal to A2 V2, right? This is our mass conservation. So whatever mass is coming from smaller pipe, same mass is going out in the through the bigger pipe. So from here, A1 is pi by 4 D1 square V1, pi by 4 D2 square V2. Pi by 4 will get cancelled. And Therefore, you know, v1 by v2 is nothing but d2 by d1 whole square. Actually, there is one very nice subjective question also on this. We will take it after this question. Anyway, so yeah, now it is asked that you know, in this question it is asked that get the answer in terms of v1. You can get it in terms of v2 also, but let's stick to the question. It is v1. So we want to eliminate v2 from the hx expansion formula, right? So how to eliminate v2? What you can do is keep v1 as it is, and from this equation number 1 you put the v2. So now v2 will become, if you do the ulta thing, it will become d1 by d2 whole square into v1 divided by 2g as it is. That remains as it is. Okay. So if you just simplify this, you will get v1 square by 2g common, and there will be one factor which is 1 minus d1 by d2 whole square. So here now whatever is the like values given in the question, you can put and get the answer. So here d1, which is smaller dia, which was given as 6 cm, and d2 as 12 cm. So basically the ratio is double. So d1 by d2 if you take, it is nothing but 1 by 2. Therefore your expansion head loss due to expansion will be v1 square by 2g 1 minus 1 by 2 square. So that will be 1 by 4. 1 by 4 cos 1 by 2 cos square 1 by 4, 3 by 4. So okay, 1 second. Array, there is a square term, right? So yeah, you should not do that. This is not correct. Yeah, the rest of it is correct. I missed the square. So anyway, today maybe I'm off my game. But yeah, there is nothing wrong in the derivation. It's just that the whole bracket has a square, so you cannot just take v1 square by 2g as a common. You can keep the formula as it is. There is no problem here. If d1 by d2 is 1 by 2, you will have or maybe if you just want the formula, this 2g remains as it is. You can take v1 common here itself. It will be 1 minus d1 by d2 square, and it will be whole square. Oh, I can take common then, right? Yeah, so if you simplify, you will just get something like this. So earlier thing was also correct, only I missed the square. Yeah, so basically you put d1 by d2 as, so v square v1 square by 2g as it is. Then you have this double bracket. So outer bracket also has square, and inner bracket also has square. So d1 by d2 is half, so it's a square also. So this is v1 square by 2g into 3 by 4 square. So that will be 9 by 16 into v1 square by 2g. So this will be your formula. The main mistake that students make here is what happens now when you study this formula for more time, you forgot, because mostly it is, sometimes like mostly the fluid goes into the atmosphere. So typically student only take v square by 2g, but in expansion it is v1 minus v2 square by 2g. So this is there. Let me just check the answer. I think it is correct only. Yeah, correct. There is one very nice question. Before that, let me just see if anything I'm missing here, because mostly minor losses this thing will be there, but there is one subjective question also, very nice question. Let me just get to it. Mm, 05. Yeah, so 1 second. Like, see, uh, if you want to solve objective questions, they will be like typically this type, or what they will do, they will give you geometry like this, the complicated geometry, and then they will tell you to, you know, if I have some space here only, yeah. So what happens is typically these are your minor losses, right? So your total frictional loss will be frictional loss major, that comes from the FLV square by 2GD terms, and then there will be some minor losses which will be this expansion entrance and loss due to bends. So okay, you calculated that, but this is comma, okay. So what happens typically at the end of the day, you have to solve some problems, right? Maybe I can take that type of problem one, but I mean that is quite straightforward is what I feel, but let me see if I can find some one second. That straight type of problem is there or not, let me see. Yeah, no, it's not there, but what I'm trying to say is, let's say, actually I should have completed it here only, because you know, okay, I'll write at the top because we have some space here. So see, you have 2 points, right, which are let's say point A and point B, which are here. A is just at the entrance and B is at the exit. So you know that there are some major losses, minor losses in between. So what you do, you calculate the total, which is HF of minor plus HF of major. So you get the total frictional loss. Now, between point 1 and 2, you can apply this. Between A and B, applying conservation of mechanical energy, you get basically PA plus VA square by 2G plus HA equal to PB, VB square by 2G plus HB into plus HF. So basically this is Bernoulli equation plus some frictional loss. So I see, I am not calling it as Bernoulli equation here because, see, if you remember the assumptions that we used for Bernoulli's equation, one of the assumption was there should be no viscous dissipation, right? It should be along a streamline and there should not be no rotational elements. I have clarified at that time that in boundary layer or in viscous fluids, you cannot apply Bernoulli equation, but you can apply conservation of energy. That is valid everywhere, right? And since here we don't take any temperature changes, it is a conservation of mechanical energy. So between point A and point B, you can apply Bernoulli equation with some frictional loss. So this equation is called as it is a conservation of mechanical energy, but some people call it as a some people call it as a modified Bernoulli equation also. That is okay. That terms you can use whatever you want, but it's not a Bernoulli equation. You can call it as modified Bernoulli equation, or safest choice will be to call it as conservation of mechanical energy equation. So basically you calculate HF, you put back into the conservation of mechanical energy equation, and then you solve the problems. So like that is the complete thing about this. There is no additional thing now. So we'll take one nice subjective problem based on this. This was asked in engineering services exam in 2008, but this is good problem. It will maybe, like, if you get the hang of these things, you know, other type of problems from this section will be easier, is what I feel. So let's do that. Here also you have sudden expansion like this only. I'll just copy the image. The same thing is there. So same sudden expansion is happening between two diameters D1 and D2. So now it is asked that question is, at what ratio of D1 by D2 would the differential pressure between like inlet and outlet of sudden expansion be maximum? And what is the corresponding head loss and differential pressure head? So I think this is like the most advanced level of problem that I've come across from this section of minor losses. Anyway, the thing remains same. We know that head loss due to expansion is nothing but V1 minus V2 square by 2G. Now, since the question talks about, what is the value of this D1 by D2, so that the pressure difference between inlet and outlet of the expansion be maximum. So let's say we can take inlet as here, very close to the actual geometry. So therefore there are no other losses, only the expansion losses are there. So between points 1 and 2, we can applying conservation of mechanical energy equation between 1 and 2. So what you get? So there will be some pressure at one, then there will be some velocity head. So it is P by rho g, this formula. Otherwise the units won't match. So this is PA by rho g, PV by rho g. So everything is in terms of heads, right? So therefore it should be P by rho g. Same thing here also. You take P1 by rho g, some datum Z1, P2 by rho g plus V2 square by 2g plus Z2 plus the expansion loss rate. So now we know that these two points are at the same datum height, so Z1 and Z2 will cross off, and we will do one thing. We will shift the pressure terms on one side, so we will have P1 minus P2 by rho g will be equal to V2 square minus V1 square by 2g plus head loss due to expansion. So we are just rearranging the terms, and we'll put the head loss equation formula from equation 1. So we will have V2 square minus V1 square by 2g plus V1 minus P2 whole square by 2g. So yeah, like that. Two P1 minus P2. Okay. So this is the thing. Now we are asked the ratio of d1 by d2, right? So we have to again, we know the flow rate is constant, so it will be pi by 4 d1 square v1 equal to pi by 4 d2 square v2. So same thing. So you will have, v2 by v1 will be equal to d1 by d2 whole square. Now we have to use this information in equation number, let's say 2. So, but before that, it will be better if we take, something's common. So what should we do? Yeah. So before going there, it is better to let's assume d1 by d2, this ratio, as some variable x, so that our life becomes easier. Therefore, v2 is nothing but x square into v1. Same thing, which is written here. So now you can do one thing. You can put this into equation number 2. So what we will get? Therefore, P1 minus P2 by rho g. Okay, let's solve the whole thing. We'll see. So we will replace, let's say, V2, so that we will have the on the LHS we will have only V1. So first term V2 square. So V2 square is x power 4 into V1 square minus V1 square as it is divided by 2g. This is our first term. And second term is it's V1 minus V2, right? So yeah, so you can write V1 minus V2. V2 is x square V1. So it will be x square V1 whole square divided by 2g, right? Now we can take V1 square by 2g common. So here it will be x power 4 minus 1 will be remaining from the first term. And from here you will have 1 minus x square whole square. And this is your P1 minus P2 by rho g. Okay. So I can simplify these terms, right? So what it is basically x square minus 1, x square plus 1, the first term. And maybe I should write this. So this first term I can write it like this. And second term I can write x square minus square by, it is same thing, right? X square minus 1 whole square. So then I can take x square minus 1 common. So it will have x square plus 1 and plus x square minus 1. So therefore it will be x square minus 1 into 2x square. So something like that we have. Now again, same thing. If you want to maximize this pressure difference, we want x such that this delta P pressure difference is maximum. So again, for that we have to take the first order derivative. So therefore, and here the derivative can be taken with respect to x because v1 is constant. Here we need to take the derivative with respect to x of this term p1 minus p2 by rho g. So v1 square by 2g will be common because it is not function of x. We will have this term x square minus 1 2x square, and we will equate it to 0. Correct now? So yeah, I can further simplify this actually. I don't know why I did not do that, but let me just get some space. So here also I can do that, right? I can multiply by 2x square. I am saying here in this formula, I can take 2x square in the inside, right? So I will have 2x power 4 minus 2x square. So basically this is the final simplification. So here also it will be 2x power 4 minus 2x square equal to 0. So yeah, so now we'll take the derivative. So 2x power 4 that is 8x cube minus 4x equal to 0. So you can have x square common, x common. In bracket you will have x square minus 1 equal to 0. There will be 2 here remaining. So the solution will be x equal to 0 or 2x square minus 1 equal to 0. This is not practical because d1 by d2, which is x, it cannot be equal to 0. That means there is no d1. So d1 cannot be equal to 0, right? So this will give you the solution. So here it is x square is equal to 1 by 2. Now here also you have two solutions. X equal to 1 by 2, 1 by root 2, or x equal to minus 1 by root 2. So this is also not feasible because diameter ratio cannot be negative. So therefore, we have only one equation, x equal to, which is d1 by d2 is equal to 1 by root 2. That will give you the maximum pressure drop across this pipe. So this is the main crux. Now, as I said earlier, you can take the second derivative just to check that it is maximum or minimum. So if you do that, if you take second derivative of P1 minus P2 term, so basically it is taking derivative one more time of this you had this 2x cube minus x. Basically 2x cube minus x का और एक बार derivative लेना पड़ेगा. Then it will become 6x square minus 1. Correct. Now you have to see whether this quantity is positive or negative for x greater than 0. Because x is our ratio of d1 by d2, right? And we know, and x is always greater than 0. So therefore, the second derivative is always greater than 0. So therefore, d1 by d2 equal to 1 by root 2 will give you minimum P1 minus P2 by, I think it is rho g. Yeah. So, but yeah, see, this is minimum because, see, what typically they ask is, when there's a pressure difference, so this is minimum of this, so this is maximum of P2 minus P1 by rho g. So, let's see, there is no change in the solution. The only thing is, we have solved this problem and we have taken P1 minus P2, right? But when you say that I am taking a pressure difference, one second, I am taking a difference between any two quantity, it is typically final minus initial. So it will be P2 minus P1. So therefore, it is the same thing only. Don't get confused here. So if you want P2 minus P1, this D1 by D2 will give you maximum P2 minus P1 and it will give you minimum P1 minus P2. So think same thing only. So that is one part. Now they have asked what is the, they have asked some additional things, right? Yeah, what is the corresponding head loss and differential pressure head? So basically, expansion loss max will be.
So you say this is minimum is this minimum is equal to maximum, same thing it is certainly.
No, minimum, let's say, see, minimum of P1 minus P2 is same as maximum of P2 minus P1. That is what
yeah, that way, yeah.
Okay. So now you have to just plug it in the formula. It is V1 minus V2 square by 2G, right? And we have simplified second term. It was V1 square by 2G into 1 minus x square whole square. So now you have to put x is 1 by root 2. So x square will be, so it will be V1 square by 2G as it is. X square will be 1 by 2. So 1 minus 1 by 2 will be half its square. So it will be 1 by 4 into V1 square by 2G. Yeah, so that is correct. That is your maximum expansion head loss. And then they have asked what is the value of P2 minus P1. And they have asked head. So this will be maximum value. Now, I mean, these terms only, but we have to take P2 minus P1, right? So if you take P2 minus P1, it will be V1 square minus V2 square V1 square minus V2 square by 2G plus maximum head loss. So again, same thing. Here V2 is x square V1. So this becomes V1 square by 2G 1 minus x power 4. And you have this 1 by 4 V1 square by 2G, which we calculated from the last line. So x is 1 by root 2. So x square is 1 by 2. X power 4 is 1 by 4. So 1 minus 1 by 4, 3 by 4. One second. Am I doing anything wrong here? Maximum is coming to be 1 by 4 VE 1 minus x square whole square 1 by 4. This will be 1 minus x power 4, which is higher. V1 is higher, right? Yeah. So this quantity should be positive. So yeah. So it is V1 square by 2G 1 minus 1 by root 2 power 4 plus 1 by 4 V1 square by 2G. 1 by 2, 1 by 2 ka square is 1 by 4. So this is 3 by 4. Correct only, right? So this will be V1 square by 2G. 3 by 4 plus 1 by 4 will be equal to V1 square by 2G. 1 but here they are saying it is half. Have I done any mistake? No, because this is 2x square minus 2x power 4 V square by 2G. 2x square minus एक second. 2x square minus 2x power 4. X square is 1 by 2. 2 into 1 by 4. This is 1. 1 by 2. 1 by 2 they are saying. One second. See, here we had simplified everything, right? So we were getting, let's say, number this equation as, let's say, equation 3. So if you take P2 minus P1, it will become 2x square minus 2x power 4. So this thing becomes V1 square by 2G 2x square minus 2x power 4. If you do that, this becomes V square by G. X square is 1 by 2 minus x power 4 is 1 by 4. So this whole thing becomes 1 by 4. So this becomes V1 square by 4G. We are getting 2G here. My question is, how come? This is correct. V2 is x square V1, right? V2 is x square V1. That is also correct. So x power 4. One by root 2 square will be 1 by 2, 1 by 4, 3 by 4. See, this is the correct way. I'll recheck it later, but in the interest of time, so we have this as v1 square by 2g into 2x square minus 2x power 4 from equation 3, and if you solve it, you get v1 square by 4g as the answer. So this is your final answer. I think I made some calculation mistake somewhere on the line, but yeah, the rest of thing is correct only. Here somewhere it's going somewhere else only. I'll check it later, but minus x square minus x square. Yeah, I cannot take it as 1 minus x square. That is wrong, because then this will be, there will be one negative sign, right? Yeah, so this is correct only. This part is correct. The calculation that I did earlier was wrong. There was some one negative missing. Anyway, so that is the whole thing about the minor losses. I hope this subjective question will help you understanding. But this is the maximum that can be asked. So now next part is this, they call it as equivalent pipe, something like that, or series parallel pipes. So basically there will be two pipes in a series, and if you want to replace them with a single pipe, what should be the dimension of that pipe? Basically, what should be its length or what should be its diameter for certain criteria. And if they are in parallel, if you replace them, what will happen? Like that. So basically, if you have seen, like yeah, so let's say you have one pipe. I'm not drawing the pipe because that takes a lot of time. Let's say you have one pipe, it is getting divided into 3 pipes like that, and then again it becomes a single pipe later. So these 3 pipes which are shown by a line here, they are in a parallel connection, so like that, and each pipe will have some F1, L1, D1, right? It will have F2, L2, D2. This will be F3, L3, D3. And now the question is asked that if we, let's say these points are connected between point 1 and 2, the question is asked that you don't want 3 pipes, you just want one pipe between point 1 and 2. So what will be its F equivalent, L equivalent, D equivalent? Typically this F value, they assume it to be constant in a sense that it will be equal to F1, F2 or F3, any one of them. That information is typically given in the question, and that you can use to solve the problem. But if you want to find such equivalent pipe, what you have, the equations that you have is, you know that the flow rate which was flowing through pipe Q, and Q1 was going here, Q2 was going, and Q3 was going here. You know that from mass conservation, these all should add. But since these pipes are in parallel, head loss across all of them will be same. That is the main thing, and it should be equal to same across the equivalent pipe. So that is one thing. And what is the head loss formula? Neglecting the minor losses. If you take the minor losses, this becomes very complicated. So you have FLV square by 2GD as the general formula, right? But typically here we talk in terms of flow rates. So what we do, we modify this formula and we make it as, so we know Q is equal to some area will be there, pi by 4 d square into velocity. So we put that in the HF formula. Therefore, we get HF as you will have FL by 2GD as it is. V square will become Q square by pi square into 16 into d square, d power 4. So basically, if you like this 2 and G and pi square and 16, if you take and multiply them, you get FLQ square divided by, there is one constant which is 12.1 into d to the power 4. So typically we use this. And in series connection, we have Q is equal to Q1 plus Q2 plus Q3, right? So from here, you have Q as equal to HF into this 12.1 power d power 5 divided by FL, and everything is under square root. Okay. So basically, if you put it in 1, what you will get is one second. HF is this, Q is this, from 1 and 2. Yeah, so basically what you get is HF for equivalent pipe into D of equivalent pipe power 5 divided by F equivalent, L equivalent. So this will be under root, and same, these three terms will be there. So you will have HF1 12.1 into D1 power 5 divided by F1 L1. Same thing again, HF2 12.1 D2 power 5 F2 L2 plus same thing HF3 12.1 D3 power 5 divided by F3 L3. But we know that from equation 2, this HF, all HFs are same, so they get cancelled. These all HFs, they are same since this is a parallel connection, so they get cancelled. And this 12.1, here also there will be one 12.1 value, so these constant also get cancelled, and what you are finally remained with is root of D equivalent power 5 divided by F equivalent L equivalent is equal to D1 power 5 divided by F1 L1 and so on. So how many number of parallel connections you have, that many terms will be there. So one question is there that in the question it is given that there are n parallel pipes of same length and dia and frictional coefficient, frictional factor between them. There are some n pipes are there, and what will be the equivalent dia of a single pipe of length L that can replace these n pipes. Assume f of that equivalent pipe f will be same as each same like parallel pipe f. So in this case, therefore this equation star reduces to, what will it reduce to? We have equivalent pipe power 5, f equivalent is same as f, and the length of the pipe is also same. The equivalent pipe that we are designing, it should also have same length as the parallel pipes. It is given in the question, and same, there are like n pipes, so this will become f1 l1, and this should not be d1, this is just d power 5, and same thing is there n times, because there are n pipes and all of them have same dia, same f, same l. So if you add them, you will get nothing but n times the same square root of d power 5 fl. So now if you simplify this, so ff will get cancelled, ll will get cancelled, and you are remained with these terms. So that can also be simplified. Therefore, you can take square on the both sides. So you will have equivalent dia power 5 will be equal to n square d power 5, right? Then you take the fifth root. So therefore you will have dq, which will be n power 2 by 5 into d. So that is nothing but n raised to 0.4 into d. So this can be one simple 1 mark question. Okay. So now similarly, one case is the parallel pipes, another case will be series pipes. So series pipe connections. In series pipes, so basically what happens is
this is general formula, digital. This is n to the power 0.4 into d.
General formula only if the all pipes in the parallel connection are same of they will have same L, D and F. If they have different,
have same HF for every all pipes, sir.
This is these equation 1 and 2, they are true for all the parallel connection pipes irrespective of their L, D, etc. Yeah. But this result, which is n power 4 into d, n power 0.4 into d, that is a special case when all the parallel pipes are having same F, L and D, and the equivalent pipe also has same L. So that is a particular case, but equation 1 and 2 are valid for every case. Yeah, and in series what happens? Let's say you have one pipe here, then you will have one pipe of F1, L1, D1 lengths here. Then let's say you will have another pipe between A to B of F2, L2, D2, and then maybe you have third pipe between B to C of F3, L3, D3. Now you have to replace this with a equivalent pipe. So only one pipe instead of three pipes in series with some pipe, and these length and diameter are unknowns that you need to find out. Here, we know that whatever is flowing, whatever liquid is or whatever fluid is flowing through pipe 1, it will be flowing through pipe 2, pipe 3, etc. Right? So whatever, how many series pipes are there, same flow rate will be there through all of them. But the head loss through the equivalent pipe should be same as the head loss in the first pipe plus head loss in the second pipe plus head loss in the third pipe, and so on. However, like if there are n pipes in series, so whatever is head loss between all of those pipes in series, that should be equal in the head loss through the equivalent pipe. So these two are your, let's say this is equation 3 and 4. So these are valid for all cases in series case. So now it's actually simple. And yeah, this will be equal to the this flow rate. 1 second. That will be also equal to the flow rate through the equivalent pipe. That's how you conserve the mass calculated. So if you do that, you can just write this as F equivalent L equivalent Q square divided by 12.1 power D equivalent power 5. And here it will be F1 L1 Q square L else F equal to. Someone's background noise is coming. Please, can you mute yourself? Yeah. So now this constant goes because it's constant in all of them. Q1, Q2, Q3 are same as I highlighted in the equation number 3. So that also goes. Here it should be Q equivalent. But anyway, it gets cancelled. So basically what you are left with is FQLEQ DQ power 5 is F1 L1 D1 power 5 plus F2 L2 D2 power 5 and so on. How many are there in the series connection? So this is the general formula for this thing. So here again I can make one question here itself only. There are n similar pipes in series. What will be the equivalent pipe diameter assuming same L and friction factor? So then this equation, let's say equation circle, reduces to, so F is same, so F I can write, okay, I can just copy it, that will be better actually. So this will repeat for n times because there are n pipes in series and they all have same F, L, what did I do, sorry. So they all have same L1, right, and this length is also same, it is given in the question. F is also same, so you will have something like this type of equation. So if you simplify, this becomes n times d power 5, correct, because the numerator terms will go away. Therefore your d equivalent will be nothing but d divided by n raised to 5th root. So basically it will be n raised to 0.2. So basically you will have n minus 0.2 into d. So like that. Yeah, then there are like, some questions are there in which, you take combinations of series, combinations of parallel connections. Those all we can solve. So basically, like general analogy with electrical circuit can be drawn, which is basically in an electric circuit you have a power source or voltage source, then you will have some load which is nothing but a resistance, and some current will be flowing through it, right? So this is the typical electrical circuit. Same analogy can be drawn in series parallel connections also, where you will have some frictional loss which will act as the load in your system, and there will be some not head, there will be some uh, capital H, total head across which the fluid flows, and the flow rate is the current, like a current parameter. So this is like a general, if you want to remember it that way you can remember, because when there are like series parallel connections, it is better to draw the this thing, uh, what you say. Maybe I can take one example so that you'll understand. So you have a flow circuit uh, which is like this. Let's say you have one pipe. So I am drawing pipe by such a symbol here, because otherwise it is difficult for me to draw. So you have a pipe, and then in the same circuit you have a parallel connection. There are two pipes in parallel, and then they are like, there is a large tank with total head of capital H, and some flow is flowing through Q. So for example, this will be having length L1, diameter D1. This pipe will be having L2, D2. This will be L3, D3. And for simplification, assume that all friction factors are same. So this is F, here also it is F, here also it is F. It can be different, but for the sake of solving the problem easily, we are assuming them to be same. So now the question is, if I want to reduce uh, this pipe arrangement, flow arrangement in like what will be the equivalent pipe dia, which is dq, assuming let's say L2 and L3 are equal, which is equal to L1 by 2. मतलब L1 के half है, L2 and L3 are half of L1, and that is nothing but equal to equivalent. So basically you want to replace it with the equivalent pipe, which will be equal to L2 and L3, which are nothing but half of L1. So this information is given. So now you can solve it using the analogy with the electric circuit. So here, as I said, that the the two pipes are in parallel. So if you first solve that, so what happens? So I will first solve this parallel thing. So here we know that for parallel we have this formula, right? Which is, yeah, this formula. Maybe I can copy. So now have this formula, and there are only two parallel connections. So this will be become D2 F2 L2. This will be D3 or 5 F2 F3 L3. Because these numbers are L2 and L3, that's why the subscripts change to 2 and 3. And let's say I give it as some F dash values here, because yeah, and D1, D2, D3 are same. See, this question I'm framing from my mind, okay? So don't think that, okay, he's doing something else. But you understand the point, right? This question can be reframed in different ways and it can be given to you. We can take one solved actual problem also, which is similar to this. But before that, I'll just give you some flavor of the problems that can be asked from this variety. So now we have D2, D3 same. So, and this FF will get cancelled because all F's are same. It is given in the question. L2 and L3 are also same. D2 and D3 are also same. So, this thing just becomes 2 times, let's say D2 power 5 L2, because L2 and L3 and D2 and D3 are same. So now we have a pipe. So these parallel pipes can be represented like, now the problem is in this equation, let's say we call it as equation number 5, DEQ dash and LEQ dash are unknowns. So these are basically the equivalent diameters if I replace two parallel pipes with single pipe. These are unknowns, right? And we only have one equation to solve for it. So yeah, that is the problem. Maybe I can give you some easy work around it. Is assume this LEQ dash equal to L2. Just to simplify the things, okay? You can argue that you are not giving us the harder versions, but typically they are not that hard, because if you have all the values, there will be some sort of constraint will be given so that you can find DEQ dash and LEQ dash, something will be there. Here it is at same thing. So therefore DEQ dash will become 2 to the power 1 by 5 no 2 to the power 2 by 5 into D2. So basically your circuit will now become like this. You will have one pipe which was already there, which is F L1 D1, and now you have one pipe here which will have DEQ dash and LEQ dash, and F is also there because F is same for them. So it will be like something like this, same flow rate, same total head. Now you can further simplify this. Now there are two pipes in series, right? So for two pipes in series, we have the formula which is where is it? Yeah, this one, FLD power 5. So here F equivalent D equivalent power 5 divided by L equivalent, correct na? Oh no, L is upper. L D Now it will be here F1 L1 D1 power 5 plus F equivalent dash L equivalent dash divided by D equivalent dash power 5. So we know that F are same, so they will get cancelled. Now here we know this is L1 D1 power 5. This becomes L2, and this is 2 to the power 2 by 5 into D2. And here again you have L equivalent, D equivalent power 5. So now here and also we know that L1 is 2 times of L2. So I can replace this with 2 times of L2. So D1, D2, D2, D3 are same. So therefore this becomes 2L2 by D1 power 5 plus L2 by 2 to the power 2 by 5 into D1. So you can solve this, right? I mean, if you don't have the values, you can't, but the values will be given to you in the question. So that is not a problem typically. So like that, I think it's better to take one example, because without values you might be getting confused. So there is one example where you can understand all these things. Let me just get to it. Uh, 246. Yeah. So there is a tank, not a tank actually, I should call it a reservoir, because if you say tank, its value, the head will change, but if it's a reservoir, it's like a dam, so it won't change that much. So there are two reservoirs like this, and it will have, these are the free surfaces. There is a difference of 15 meters between their free surfaces. And there is a pipe connecting to it. It has diameter of 300 mm, and the length is given as 1 kilometer. The pipe length is 1 kilometer. So the first question is like, it is a multi-part question. First question is find the flow rate through this pipe. So there will be flow rate from here to this side, right? Because head difference is higher here. So now see, only this is asked, right? So, and F value is given as F value is given in the question as 0.02. So that is also given. So now they have not mentioned whether we need to consider major losses or minor losses. So you know, we can solve the problem by considering them and neglecting them. We can make it as a case study because somebody asked in the initial part, right, that I think what somebody only one student is asking. So why we call them major and why we call them minor losses. So we can clarify that here. So so like see, the flow will take place till you know you have enough head to overcome the frictional head loss. Right? There is no other driver here, no pump or anything is there. So in this system, the flow will be like this 15 meters of height that is given, that will be equal to the uh, head loss to the due to the friction. Then only flow will take place, right? So uh, you can directly you know uh, let's say first we neglect minor losses. Okay, now then in that case your 15 meters of head will be used to overcome the friction. So that will become FL V square by 2G T. So we have all the values. F is 0.02, L is 1 kilometer, so 1000 meters. V is the unknown, and 2 into 9.81 into D is 0.3, 300 mm. So if you solve this, you get velocity as 2.101 meter per second, and therefore flow rate, which is Q, is nothing but pi by 4 d square into V, right? And d is also known, V is also known now. So if you do that calculation, you will get 0.48148 meter cube per second. So this was the first part of the question. Now, let's say we don't second part is let us consider minor losses as well. So in that case, your head will be used for FLV square will be there. Let me call it as V1 here because it may change. Plus there will be one entrance loss which is at the bottom of a bigger reservoir, which is here, and there will be one exit loss which will be here. Other than that, there are no losses, right? So entrance loss will be 0.5 V1 square by 2G, and exit loss will be V1 square by 2G because V2 is 0. It is going in a reservoir, so there will be 0 velocity there. So basically, you will have this equal to, if you take V1 square by 2G common, you will have FLD plus 1.5. Okay, now see here only you can realize if I calculate this FLD parameter, which is nothing but 0.02 into length is 1000 and it is divided by diameter, which is 0.3. If I do that, what do you get? So this is 0.2 into 1000, so 200 divided by 3. So 200 divided by 3 is how much? 66 something, right? 1 second. 0.02 into 1000 divided by 0.3. Yeah, so V1 square by 2G becomes 66.67 plus 1.5. So the point that I was trying to make earlier is, see, the contribution due to FLV square by 2GT term is 66 times more than 1 point times. So basically, minor losses are basically very negligible, is what I'm trying to say. So minor losses, major losses are 45 times more than the minor losses here. So more or less, if you do the calculation, you will get V1, which is approximately same to the V only, because minor losses will not be that high, since minor losses are small. So that is one point that we figured out, that the reason why they are called as minor losses is because when the length are too long and diameter is too small, for such pipes, this FLV square by 2GT terms become more dominant than the minor loss terms. So that is there. Then there is a second part to this question, which is relevant to our discussion. Uh, okay, I'll take 5 more minutes and we'll stop maybe. And there are some other questions in the chat box. We'll take those. So they have said that now that pipe is they want to increase the discharge between the two reservoirs. So to do that, what they did is, there is earlier pipe of 300 uh, 300 mm dia. It is there, but for half of its length, they have put. Oh, I should have drawn it slightly bigger. Yeah, they have put one more pipe of they have put one more pipe of same. So now instead of going through one pipe, the flow is flowing through two pipes, like that. So earlier, if I say this is point A and point B, so this is still point A, still point B, but now there is one more there is one more pipe across this cross section, like that. So that is the new problem. This pipe also has a same diameter of 300 mm, and this pipe is given for half of the length, which is 500 meter. And they have said that here they have clearly mentioned that neglect minor losses, because here it will become complicated, right? Because you have a diversion in the flow, so like that. That is out of scope of this syllabus. And here also take same F, which is 0.02 for both the pipes that they have given. So they have asked find percentage increase or decrease in discharge. So this is the question. So now there was Q flow rate flowing through one pipe, let's say Q1, because we don't know whether increased or decreased, and now it is split into two parts, which is Q2 and here it will be Q3, right? So we know that from mass conservation, Q1 will be equal to Q2 plus Q3. That much we know. And now see, all the pipes are having same diameter, so they will have same area. So if you consider that, area will get cancelled, since all pipes have same dia. Okay. Now, one more thing that you can note here is length is also same. So if that is the case, see these Q2 and Q3, they are in parallel, right? So for parallel pipes, what do we have? For parallel pipes, the head loss will be same through all of them, HF, H2, H3, right? So we know in parallel pipes, HF2 will be equal to HF3, right? And formula is FL2 Q square, let's say Q2 square, divided by 12.1 D2 power 5 will be equal to FL3 Q3 square divided by 12.1 D3 power 5. But L2 and L3 are same, which is 500 meters, and D1, D2 and D3 are also same, which is 0.3 meter. So from this equation, therefore we get Q2 equal to Q3, and therefore Q1 is equal to 2 times of Q2, and therefore V1 is equal to 2 times of V2. That means the velocity in the two pipes which will be same, and that will be half of the velocity in the first half of the pipe. So this important information we got. So again, now what will be the total pressure, total frictional head between A and B? That will be equal to 15, and that is nothing but addition first head in the first half of the pipe, and then there is second head, because second and third pipe will have same drop, right? So only one term we have to consider. So what will be the first HF1? It will be FL1 Q square, let's say Q1, 12.1 D1 power 5, and for HF2 it is FL2 Q2 square, 12.1 D2 power 5. We know that Q1 is 2 times of Q2, and or maybe rather than using this, we can use simple formula, na, FLV square wala. So because we know the velocity relation, na, so that will be very easy. So that will be FLV square by 2G D1, FLV2 square by 2G D2. So we know that V1 is 2 times V2, and D1 and D2 are same, 0.3 meters. L1 and L2 are same, which is 500 meters. So NF is 0.02 given in the problem. So if you do the maths, only unknown is V1. So you get V1 as 2.66657 to be precise, meter per second, and V2 will be half of it, which will be 1.329 meter per second. So if you calculate the flow rate, let's say Q2, that will be A2 V2, and if you put the values, you will get the flow rate as one second. Why are we calculating V1? We can calculate only Q1, right? Because that flow is only getting divided into Q2 and Q3. So Q1 will be A1 V1. Then if you do that, you get the answer as 0.188 meter cube per second. Whereas with single pipe, Q was, we solved it in the first part. With single pipe, Q was 0.148 meter cube per second. Therefore, the flow rate is increased, but they are asking in the percentage, right? So for that, it will be 0.188 minus 0.148 divided by 0.148, because initial value we have to take in the denominator. It will be approximately 26.5%. So this is one type of problem that can be asked between series and parallel combination. Okay, so we'll stop here. There were some questions posted by student in the chat box. Let me just see them before we close. One second. Chat box. It is not opening here. One second. Yeah, so Pradeep was asking this. Okay, so first question is, here they have given you U and V, W is 0, so it is a 2D flow. V and theta are constant. We need to find the equation for the streamlines. So, yeah, I mean, I had given you the formula earlier, right? Okay, maybe quickly I'll solve. You can see the formula later. What was it? U V cos theta, V sin theta. U was V cos theta, V was V sin theta, and the streamline equation they want, right? So for streamline equation, this is in the cylindrical coordinate, right? I mean, typically we have this equation for streamline, which is dx by u dy by v, but here they are using some cos theta sin theta terms, right? So one thing is, you can convert this cos theta as y by root x square plus y square, sin theta as x by that type of thing, but that will be too tedious. I can try, but I don't know how much time will it take.
Sir, apparently it looks like 10 theta already, actually, because once you see this, apparently it looks like cos it will be 10 theta, like C, y is equal to x 10 theta by C plus C. Because once you
one thing we can do, see, instead of, there is actually a formula for cylindrical coordinate system also. Let me just check if I can find it. This dx by u is for Cartesian coordinate system, na?
yes, sir. Yeah.
So for cylindrical, let me just check if I have the formula with me. It should be something similar only, but no, for cylindrical coordinate, I don't think I have it with me. But if not, let's convert it. So you can write, you can define one triangle, and you can define theta here. This will be your x, y, and this will be your radius, which will be constant, x square plus y square, because this is a typical circle equation only. So sin theta will be x by r, cos theta will be y by r. So if you put that, you get u equal to v y by r, v equal to v x by r. So if you put that here now, it will be dx by v y by r dy by v x by r. R gets cancelled. Anyway, it is a constant. V is also constant given in the equation. So now it becomes x dx y dy. If you integrate it, what do you get? X square equal to y square plus some constant by 2 will be there. So basically it becomes x square minus y square equal to some constant. But we want the equation in terms of theta, right? So x square is nothing but r square sine square theta. Where did v go? So x is r sine theta, right? So r square sine square theta minus r square cos square theta
Yes, excuse me, sir.
Hello?
Hello, sorry for the interference. Sir,
Yeah.
instead of doing like that,
Mm.
take value u equals v cos theta, v is equal to v, v sin theta, then that will
Mm.
give y is equal to x into tan theta plus c. That's all.
Mm.
For a streamline equation,
Yeah.
dx
Yeah.
u equals dy by v,
Mm.
substitute the value of u equals v cos theta, v
Yeah.
equals v sin
Understood.
theta,
Understood. Yeah.
for
Understood.
dx is equal to tan theta.
Yeah. But the doubt that I was having, and still I am having, is, see, this is defined in a Cartesian coordinate system. This
Okay.
is this is typically defined in a cylindrical coordinate system.
Okay.
That's why. But like, I don't know the options. What are the options? Can you one second? If there is a tan theta option, then this might be
No,
very.
below is there, sir. They are already giving the options, sir. C. I must see, sir, actually, tan theta apparently, without doing anything, just write out tan. It is tan theta. But
Mm, maybe you can do that way, but why am I not getting this way? I should not have cancelled V or something.
let
But
us
still, it will
put the
be
value
there.
of x and y, sir, directly. U and v directly in this.
Oh, acha, oh, okay, okay. You are saying put U and V here, huh?
Yeah.
Okay. If I do that, okay. 1 second. Oh, we are already at 8:12. Maybe I'll see the next question. If others are easy, we'll come back to this. For 2D incompressible flows, slope of equistream line. This is the same thing I written na here. That dx by u is dy by v, na? So you can take dy by dx, which will be equal to, I think, v by u. V by u should be the answer for this.
So minus v by u, sir, plus v by u. So minus v by u, is it not?
Why minus? See, this is your formula, right? Which is, I'll highlight. This is the formula, right, for streamline. So if you want,
Yes, sir.
what they are asking, they are asking the slope, right? What is the ask? Slope of equistream line, bruh. So there will be no minus. It should be only, see, from here only you can write, no? Uh, dy by dx is the slope, right? So that will be v by u. Why will be there minus? I don't know. I mean, v by u sounds correct to me. So that is there. A stream function is 2x square minus y square. Is to make the,
Sir, we cannot bring the stream function thing in this place, sir, in the equistream line. Can you bring the stream function concept here also, or not necessary?
you can bring it from there also. You should get the same answer only, right? See, typically what they're done is, you define d psi as del psi by, uh, what do you do? Del psi,
Y, sir, dy.
psi by del u, huh?
Yeah.
Y
Del y, yeah, del y. Yeah.
will be like this, and del psi by del x dx, it will be like this. And for a streamline, this is constant, na? So psi is constant, so d psi is 0. So here you put,
Slightly minus, sir. It will minus d. The deck
no, no,
dx will
wait,
minus.
wait, wait, wait. So if you put here your typical things, this will be your v dx. This term will become minus u dy plus equal to 0. So from here, what do you get? U dy equal to v dx. So dy by dx, you should get v by u only, right? Yeah, it should be v by u only, because there is one minus sign here, na? Del psi by del y is minus u.
Yes, sir.
Okay, so that is there. Then yeah, so this question is also easy. You have a stream function. So basically, flow across any two streamlines is, difference between their stream functions, and you take the mod of it. So it cannot be negative, because flow rate is always positive. It's a physical quantity. It should not be negative. So
the
it
point?
should be 14. Even though by calculation it will come minus 14, I am not checking it.
It
But
could be minus 14, so I got confused.
yeah,
14,
but
yes.
there is a mod sign there,
Yes,
which
sir.
is the absolute sign. So it should be 14 because flow rate is never negative. It's not a
Yeah.
physically possible thing. Last time, so you have uv. U is function of x, v is function of t and y. Okay. So it is saying it is incompressible, right? So one thing is that you can apply is del u by del x plus del v by del y equal to 0. You treat this t as constant, and hopefully you should be able to get it. It should be straightforward, no? Because del u by del x is 0.6, del v by del y is minus a, and their sum should be 0. So a should be 0.6. So a and c options are there. And regarding b we cannot say anything, right? Because
Yeah.
it is function of some omega into t. There is no information given about t, and it doesn't matter because it's not function of y. So I think the C option should be correct.
So we cannot take b is equal to 0, sir, because t, there is no t anyway. T will be 0.
You can take b equal to 0, but then I can ask you the counter question. Why cannot I take b equal to 1?
Well, because t is 0, sir, incompressible.
No, incompressible is defined with respect to x and y. This t is a third dimension. So don't get confused there. You cannot apply divergence equal to 0 for time and all. So this t is not even time. I don't think it's time. I mean, it's not given. It should be time, by the way, because it is 2 pi rad per second. But it can be anything, right? If I take b equal to 0, okay. But if I take b equal to 2 also, my del u by del x plus del v by del y is equal to 0 only, no? So for exact value of b, some additional information is needed, which is not given.
Yes, I should see it then. It could be any value, sir.
Yeah, and coming back to the first one. Just give me 1 minute. I know we are over time.
No problem, sir.
X dx, y dy, x square. Yeah, one thing, I mean, I don't know why I did this. We can do one thing, right? Yeah, I think it is tan theta only. See, because we have x equal to r sine theta, and r is constant because it's a circle. Then dx will be r sine theta derivative cos theta d theta, and y is your r cos theta, right? So dy will be r minus sine theta d theta. Correct, huh? Why am I writing d theta again? Sorry. So if you divide dy by dx, you are getting minus tan theta. So slope should be something related to tan theta only. It cannot be cos theta and sin theta as given in the other options. But what is the fourth option? None of the above. Streamlines, huh? Can I use that? Del psi by del y. Okay. One other thing could be, maybe you can try it later. I'll close in a couple of seconds. Is yeah, one thing, as somebody had pointed out, that dy by dx is v by u. And straightforward, you get tan theta. But I have some reservation there. but maybe that is right. I don't know. I have to think on it. One more option could be, we know that u is del psi by del y, but what is it in cylindrical coordinates? I think it is 1 by r. I think it is 1 by r del psi by del r or something like that. V is del psi by minus del x. It is some theta there. R into del psi. One second, I should have this at least with me for cylindrical coordinates. Stream. In the class, was it taken? Streamline equation.
They have spoken about it. So, yeah.
Polar coordinates. String function in polar coordinate. UR is 1 by r del psi by del theta. This is 1 r del psi by del theta. This is minus del psi by del r. Okay. From here, do we get some information? So this is 1 by r del psi by del theta is your u, which is v cos theta, and this is minus del psi by del r, which is your v sin theta. Okay. And they want psi function.
But the nearest is 10, sir, so it will be 10 anyway. So just, I don't think we should think so much, sir.
Yeah, you wanted tan so badly. No, it will be tan because, see, graphically also you can think of it. So this u and v are nothing but circular, these things, circular velocity profiles, and stream function is nothing but, it is at that stream function, if you draw a tangent to the curve, you should get the velocity. So if it is a tan like this, then if I draw a tangent, velocity. Anyway, the answers are not given for this, right? Till so far. Maybe.
Answers are there below one. A, B, C, D options are there.
No, matlab, what is the correct answer?
No, sir, not from NATPTL side, sir.
D psi is nothing but del psi by del r into dr. Del psi by del theta into r d theta. Okay. See, most likely it should be tan theta only, but I'll think about it. Maybe if it is something else, I'll let you know next time.
Yes.
Okay. Since we are going over the time, we'll stop now. Maybe next time we'll see. Okay.
Thank you, sir. Yeah.
Okay. Good night. Thank you.
Good night.
See you next
Thank you so
Tuesday.
much.